This video extends the discussion of metal carbonyls to incorporate an important application of infrared spectroscopy. We'll begin with a discussion of chromium hexacarbonyl, which has octahedral geometry. As carbon monoxide in the unbound state is a neutral ligand, the coordination of a carbonyl ligand with metal does not affect the formal oxidation state. So the chromium atom is chromium in the zero oxidation state. Chromium is in group 6 of the periodic table. Therefore, chromium 0 has 6 d electrons. If we add the 6 d electrons to 6 carbonyl ligands, each contributing 2 electrons, the total valence electron count is 18 electrons. In order to accept electrons from 6 ligands, there must be 6 orbitals available. So this requires the 4s and 4p orbitals, as well as 2 of the 3d orbitals of chromium to hybridize in a d2sp3 hybridization. Specifically, the d orbitals are likely the x square minus y square orbital and the z square orbital, along with the px, the py, and the pz orbitals. The atomic orbitals of chromium which are donating electrons in back bonding are the 3d orbitals with xy, xz, and yz symmetry. As back bonding donates electrons to empty pi star orbitals, back bonding will diminish the bond order of carbonyl ligands. For carbon monoxide, we can use the IR stretching frequency of the carbonyl ligands in comparison with acetone and the free ligand carbon monoxide. As you will recall from previous courses, acetone is generally shown as a carbon oxygen with sigma and pi bond, so it is double bonded. There is a minor resonance form with charge separation, so the bond order is slightly below 2. For carbon monoxide, we typically will show a major resonance form as triple bonded. However, there are non-bonded electron pairs on the carbon and on the oxygen, and formal negative and positive charges on carbon and oxygen, which do not line up with the electronegativities of these elements. So there is another resonance form which has no charge separation but does not fulfill the octet rule on carbon. Therefore, the bond order of carbon monoxide is less than 3, but greater than 2. For several metal carbonyls, the infrared stretches have been measured. Chromium hexacarbonyl has a stretching frequency of 2,000 wave numbers. This is consistent with a bond order that is less than 3, given that this value is considerably lower than the standard for the free carbonyl ligand of 2155 wave numbers. If the metal is vanadium, vanadium in the -1 oxidation state has a formal negative charge, which is distributed throughout this complex. But the negative charge from an additional d electron in the group 5 metal center provides more electron donation for back bonding, decreasing the bond order of carbonyl. And this is revealed by the infrared stretch at 1859 wave numbers, greater than the bond order of a ketone, but probably closer to bond order of 2 than to 3. For manganese, which is in group 7, if we remove an electron so that manganese is in the +1 oxidation state, manganese hexacarbonyl has a positive charge. In this case, with a positive charge on the metal center, the d electrons are held closer to the metal, are less available for back bonding. As a result, the carbon monoxide ligands have increased bond order, and this is revealed by the IR stretch of 2096 wave numbers, which is closer to a bond order of 3. We'll conclude with some tetrahedral metal carbonyls, in which we see similar trends. Nickel tetracarbonyl is nickel in the 0 oxidation state. As a group 10 metal, it has 10 d electrons. Cobalt tetracarbonyl anion is a group 9 metal with an additional d electron, once again having d10 electron count. Notice that with a negative charge on the metal, more back bonding leads to decreased carbonyl bond order. With iron tetracarbonyl dianion, iron being group 8, -2 oxidation state, therefore D10, has even more back bonding, diminishing the carbonyl bond order much closer to 2 than for the other metal carbonyls discussed. This concludes the Module 5 video on metal carbonyls and infrared spectroscopy.